Hi everyone. So I think we've got a few attendees at the moment, but we'll just give it a couple of minutes before we start the event just to let people join. So I think we'll get started just on the ICorr slides at the moment. So thanks everyone for joining. We'll get started on these slides and hopefully if anybody else joins, they'll be in time for Kevin starting his discussion on the digital approaches to enhance integrity management. So thank you to Kevin for presenting to us on this evening. So just a couple of slides from ICorr, hopefully if they work. So this is just a slide of all of our branch sponsors. So thank you to all of our branch sponsors that we can see on the screen here. And this is our Aberdeen branch committee. So unfortunately, mailing our chair couldn't make it tonight. So it'll just be me doing a quick hosting at the start of this presentation. And our next event will be our annual industrial visit, and this will be held at Bilfinger. The details are still pending of this, but will be put up onto our social medias and via emails as soon as we have more details on this. So our presenter today is Kevin McDonald. He's a principal integrity engineer within Sonomatic's integrity team, and he's a mathematician with a PhD in computing science. He has extensive experience in data analytics and inspection planning, co-authoring the non-intrusive inspection recommended practice. As well as integrity consultancy, he is involved in technical capability development for the integrity team. Development's focus on novel applications of statistics to the analysis of inspection data implemented following both topside and subsea inspection campaigns. So I think that's all of our ICorr slides, and with that, I'll leave it to Kevin to share his slides for tonight. And as always, if there's any questions throughout, please use the Q&A button down below with anything, and we can go over this at the end. So thank you, Kevin.
Thank you. Just make sure everyone can see my slides.
Yeah, we can see
Yeah,
your
excellent.
yeah.
Thank you. Yes, thanks for the introduction. As I say, I'll be discussing digital approaches to enhance integrity management. Excuse me. Disclaimer: I've got a bit of a sore throat, so my voice goes at any point. That's why. Um, some of you who have been sort of long-term attendees to this event may remember 2 years ago I gave a talk on a inspection methodology, sort of methodology for making better use of pipework inspection data using statistical analysis and long-term data trending to provide more reflective corrosion rates and the more efficient inspection planning. This talk's meant to be a more generalized version of that, I suppose, just touching on a lot more aspects to that and how digital tools that we have can enhance integrity management in various ways. Before I get to that, just for anyone who doesn't know, so as Eli said, I work at Sonomatic, and we are primarily an inspection company providing both advanced and conventional inspection services for anybody who wants to be perfectly honest. In addition to that, we also have an integrity team, which I work in. Sonomatic are owned by a parent company called the CWL Group, who own various other companies across the world, all related to the inspection industry, some doing the physical inspections, others providing ROVs, for example, and other unmanned vehicles to facilitate inspections. But as I say, they all kind of we complement each other in terms of a group of sister companies to deliver inspection activities across the world. As you said, I work at the integrity team within Sonomatic. So within that, there are in effect three sub-teams. There's the integrity division, which I'm one of the leaders of. There's a software arm who develop software primarily for the use within Sonomatic to make our overall delivery deliverables more efficient. We do license some software, but as I said, primarily just for in-house use. And finally, there's an R&D team who, again, research primarily new inspection techniques, new methods of analysis, and those software team do have an input to the R&D side as well in terms of development of new software capabilities. The integrity services that we offer, so it's primarily to complement the inspection activities, but we do work with anybody, with any company that in terms of data, for example. So primarily through the provision of inspection planning. Before inspection goes out, we can do some advanced data analysis post-inspection and also some statistical evaluation of data in a sense, derive maximal value from any inspection campaign. So the presentation I've got is, in effect, separated into two parts. First of all, I'm going to discuss a mini digital twin and then the digital solutions for integrity management, specifically for non-intrusive inspection, pressure vessels, and AI, analytics and statistical analysis of data. I'm then going to move on to how that feeds into our data processing capability in terms of housing the data in a digital environment and then doing more with it in essence. So specifically going through algorithms to distinguish between internal and external corrosion. Excuse me. Evaluation and correction for any coating thickness variations, batch processing of data if we've got a large volume of it, and automated reporting once an inspection campaign has been completed. So just a slide is going to motivate the topic itself. So integrity management does rely very heavily on inspection activity to ensure assets fit for service. So an inspection will take place, and then the results of that will be fed into future inspection planning in terms of perhaps refining potential degradation risks for a component, maybe revising the inspection interval in terms of either extending it or shortening it depending on the findings, and various other aspects to that too. Inspection can take several forms depending on the degradation risk. So there's the more qualitative driven approaches, for example, an internal visual inspection or a remote internal inspection of a pressure vessel, and also the more qualitative approaches to, for example, non-intrusive inspection, which is an externally applied inspection to assess a condition, corrosion mapping of anything, to be perfectly honest, or then spot point regions, which is mainly for pipework inspection, but that can take the form of either manual UT or radiography. All inspection does require some form of planning to ensure that the inspection is efficient and effective. So in other words, you want to be as sure as we can be when we go off to do an inspection of what we're looking for, and the information that we have is representative of the current state of the component that is going to be inspected. Just again to ensure that we get the most accurate and meaningful results from any inspection activity. All forms of inspection do generate data. I hear a phrase trotted out a lot at the moment that there's more data being generated now than ever before, and therefore we should be making better use of it. I do agree with that. Any inspection campaign will generate a lot of data, and that data should be used to its maximum in order to get the best results from that. So given all of that, digital tools can improve the effectiveness of planning, recording, and evaluating all inspections. That's the whole motivating factor for this presentation. So a mini digital twin, I've got a definition here of a mini twin. I'm not going to read it out because it's just quite dry. But in essence, digital twin is just a virtual representation of some real world entity, be that a single component or be it multiple components. Whole platform assets, whole platform/asset twins are becoming more common. From what we see, that often doesn't meet the needs of an inspection. It's that old cliche of not seeing the woods for the trees. There's just too much information thrown at you when you're looking at an entire asset twin. So therefore, we tend to focus on a mini twin for a single component to enhance needs inspection and integrity management. Just an example of that. So I've got two examples here. One of a pressure vessel, one of a pipework circuit. Just the types of things we always create when we're doing any kind of inspection activity or inspection planning for that matter. So we've got a pressure vessel on the left, which has got some inspection data on it, and then on the right hand side there's a pipework circuit. The legend's perhaps not very easy to read, but this has been segregated into individual spot point measurement locations, and these have been coloured by the number of previous inspections that each of these has seen. So, for example, 4 is green. Anything that's grey has not seen any inspection at all on this particular circuit. But as I say, that's just an example of the types of models we kind of do create, just as a flavour for the remainder of the talk. So moving on to one of our specific topics on this. So first of all, I'm going to talk about NII, but I want to just make clear what I mean by that, because we still see that the term NII and NDT is used quite interchangeably a lot in the inspection industry. So when I talk about NII, it's one of our core services, and it's a 4-stage sort of process which is applied to pressure vessels with the aim of either deferring or replacing an internal visual inspection. So I mentioned the 4 stages. So there's an assessment to determine if a vessel is suitable to have NII applied, which, as I said before, is an just externally applied inspection to verify the internal condition. Assuming the vessel is suitable, a work scope is then developed with a specific set of criteria that the inspection must meet, and the vessel is then inspected. And then finally, there's an evaluation phase, which will assess the inspection results to ensure the inspection criteria were met. There is a recommended practice which has been written to govern this process. In essence, this was first published in 2007 by DNV. The latest version went live in February 2020. And as Neil mentioned at the start, I was one of the authors of that recommended practice. So just as a slightly more expanded overview of what the process involves. So as I said, there was an assessment phase initially, in which we will review the operating and design parameters of the pressure vessel and the inspection history to determine if it's suitable for NI. If that is the case, we would then develop or define the key inspection requirements in terms of both coverage and the most representative locations for inspection of the vessel given the degradation risks, and also define the appropriate inspection techniques that are most suited for, again, the vessel and the degradation risk associated with that. A work scope is generated, which basically produces itemized description of each of these inspection tasks in a slightly more detailed manner, just to specify exactly what coverage is required and where on the vessel that should be located. And we also can mark those locations out onto a twin as shown in the image here. It's important too that also defines the reporting requirements for the inspection teams. In other words, what they need to report back to us in terms of findings that may be of concern. Once the work scope's been produced, the inspection happens, so the team goes off on site to perform the inspection, and with an ongoing communication between both the inspection and the planning teams, just in case there's any unforeseen issues, and therefore they can be resolved as quickly as possible. And finally, there's an evaluation phase in which the results of the inspection are essentially compared against the initial aims of the work scope to determine if the NAI could be used to defer or replace the planned internal visual inspection. We can also make some recommendations on any ongoing integrity management activity, such as they may want to shorten the inspection interval, for example, or specifically, or if there's a specific area that would be beneficial of being monitored. So we've got an example here of the type of vessel, type of model that we'll produce of a vessel for doing an NAI. So 3D models are used throughout the whole process, and primarily just because of age, efficiency, and consistency at all stages. We can, as I say, we can just create the model and then deploy with the inspection team and hand it back to us once that inspection has been completed. It makes life so much easier for everybody. In addition to that, NAI does provide a cost-effective alternative, but can generate substantial amounts of data, particularly if it's a high coverage requirement for a vessel. There will be a lot of data associated with that. I've got an example later in the presentation of a vessel that's got a lot of data on it, and you'll see just the sheer volume that is generated. And that all needs to be housed somewhere as well. So it's much easier to have it on a model so we can easily see where each scan has been completed, and it's much more simple for everybody in terms of visualization to identify where each scan has been completed, particularly if there's any degradation that has been identified. But in terms of how these digital tools can aid efficiency of the NAI process itself, so I mentioned one of the things we do is review the inspection history. So within our digital tools, we can just visualize that as a timeline, which, as daft as it sounds, it can be a massive help, again, just for the sake of visualization of all stakeholders in terms of understanding exactly what the vessel has seen. In terms of previous inspection, that obviously doesn't just have to relate to pressure vessel. We can produce this for any component, but for the purposes of this example, this is an inspection history from a pressure vessel. So you can see there's been a number of different inspections. It's had some UT, so internal visual inspections, bore scope, for example. So as I say, it's just a much more simple and efficient way of representing the history in a single snapshot for all stakeholders to easily capture the overall picture. We also use it to mark up the various zones of the vessel, primarily with an ease of reviewing the threats that are applicable. We can mark up the vessel in various zones in terms of what each zone is seeing. So for an example here, we've got liquid zone at the bottom, which is constantly wetted, which would be an area that would need to be targeted by inspection. In addition, this vessel was also clad beyond a certain point, so we can mark up where the cladding is present too. That would require a slightly different inspection technique to be deployed, and may require slightly different coverage level too, depending on the specific cladding that's in place. But overall, the reason that we do this is just to, again, just make life easier and everything clearer for everybody who's going to be involved in the NAI process, both in terms of us and the client. And it's just, we can show the process flows, so that may highlight or guide us to where any areas of concern may be. Similarly, if there's any areas of known corrosion, these can also be marked up in a drawing such as this to, again, illustrate areas that we need to be targeted during an inspection campaign. Part of the NAI recommended practice also constitutes a flowchart, which guides you through three questions to determine if NAI is possible. It's yes or no, high, medium, or low, at three different categories, which at the end of it gives you an outcome on whether or not NAI is possible. So again, we have embedded that into the digital tools we provide for NAI, purely, again, make life easier. And it's much easier to capture, much more reproducible in terms of justification as to why NAI is acceptable for a particular vessel. So there's a series of drop-down menus that mimic the flowchart that's shown here on the right. So once these have been completed, it will produce a diagram similar to the flowcharts here, with the various stages highlighted that have been chosen. So for example, if we choose a high confidence in the previous inspection, well, that will be highlighted, then it'll just filter through to the remainder of the different options to illustrate whether or not NAI is possible. And we can also add in comments at each stage as well, just to further justify the decisions that were taken at each stage. I mentioned the work scope earlier, so moving on to that. So as I said, we try to be as detailed as we can when we are making when we're putting together work scopes, so that the they're as clear as they can be to the inspection team. It is important that each item is achievable. Sometimes that isn't the case, but again, access when you get to a platform, for example, could be heavily restricted that we just don't know about. Maybe it wasn't captured in photographs, for example. But we would always mark up areas on a model to illustrate where the areas of inspection that we would like to see are located. As I say, there are times when those can't be captured for multiple reasons. But again, it's just a very good visual tool to represent the areas of inspection that are required, again, for both our side and the client side, because we can hand this over to the client who then can go off and say, well, for example, there's a walkway that hasn't been captured on the model that could be used to gain a further higher elevation and therefore make life easier for the inspection team. So similarly, they could also tell us that access is heavily restricted at one location, and we need to consider an alternative. So once the inspection team is deployed on site to perform the NI inspection, these inspection results will all be populated on the same model that was created in the initial stages during the assessment and work scope phases. One thing I do want to stress here that the data that's uploaded onto our models isn't just composite images of numbers. It is interrogatable data. So in other words, it contains the waveform data that was captured during the inspection campaign. So anyone could go in and assess the data at any point to double check anything, for example, or if they just would like to reanalyze it in any more detail for whatever reason, that can be done. It's all done within our digital framework. There's a number of additional benefits to that. So we can instantly see if inspection data is recorded incorrectly in terms of geometry. So for example, if you're expecting a nozzle, inspecting around a nozzle, and that shows up somewhere that you weren't expecting it to when it's uploaded onto the model, that's very easy to change at that point. The technicians can also see patterns as they're inspecting. So if they see anything of concern, it's very easy to visualize that immediately, and they can make adjustments to the inspection area immediately if necessary. It makes life much easier and quicker for interim reporting. So in other words, just specifying what coverage has been achieved and any initial minimums that have been found. I say initial because we do provide interim reports while the technicians are on site, but they're just indicative values that they're not fully confirmed until they've done a full in-depth data analysis once they're back on shore. And finally, I see improved communication. It helps communication, understanding between the various teams, primarily because if the inspection team finds something, they can very easily just point out to us on this model. Similarly, if they get on site and they discover that they can't inspect a certain area for reasons that weren't picked up in advance, so for example, maybe the surface is worse than it was initially thought, they can again just specify this is an area that we cannot get, and they can suggest an alternative, or we can just suggest an alternative and move it for them. Again, just to make everything more efficient for everyone. So finally, evaluation phase. It's one that's often forgotten. Very often clients that do it themselves, but this is a very important phase to the NI process because it's the justification of not doing the internal visual inspection, or rather, it's the justification of using the results you have got in lieu of your internal visual inspection. So what the NI evaluation will do is review the conformance to the initial inspection plan in terms of was the correct coverage achieved, were the correct locations achieved. If they weren't, were suitable alternatives taken instead, and was the correct inspection technique achieved? And what I mean by that is, was a technique with a suitable probability of detection used? And if not, how large was the difference? With a view to doing a detailed analysis to justify operation until the next inspection. So in other words, whether or not the NAI has effectively replaced or deferred the internal visual inspection or not, as the case would be, which does happen sometimes. And again, as I mentioned earlier, we can also make recommendations in terms of ongoing integrity management that may be required. So the crucial thing here is the digital twin, again, just makes the data analysis quicker and more efficient. The inspection data, as I've shown in previous slides, it's all uploaded onto the 3D model. We use all the data from the inspection campaign. We don't just look at minimum values. We can also collect data from different zones. So, for example, if, as I mentioned earlier, if there's a liquid zone in a vessel which is showing behavior which is markedly different to the remainder of it, we can very easily just gather those scans together and treat them in isolation, in effect, because they're behaving differently. Very easy also to review cumulative thickness distributions, and I've got an example of this here. So for anyone who doesn't know, this is just a plot of inspection data. So the black curve is inspection data from a particular campaign. This is plotted on a logarithmic scale, so you've got a percentage of the inspected area on the y-axis, and on the x-axis you've got thickness values. The change in shape at approximately 9.6 millimeters, that represents transition from corroded into uncorroded. Sorry, from uncorroded into corroded material. And then the red line is an extrapolated curve. So the final point here, we can instantly extrapolate data to uninspected areas. So we can, in essence, isolate the corroded portion of material within a sample size. We can then extend the curve based on that data trend by a factor relative to the overall coverage that was achieved. So, for example, if it's 4%, will be a relatively long line. If it's 40%, it'll be relatively short. It'll be an order of magnitude between the 4 and the 40, just to make that clearer. And the NI evaluation also requires that we specify conformance levels. So again, we can easily represent those on a digital twin too. We've got examples of the various conformance levels that are achievable here. So there are 4 levels. Green is level 1 down to red, which is level 4. Green and yellow, which are level 1 and 2, would normally allow the inspection to be used as a deferral. Red and orange, which are levels 3 and 4, would normally not allow the inspection to be used as a deferral or replacement of IVI, unless there was some additional justification performed or some additional inspection was performed. And as I say, this just makes, again, the use of a digital tool just provides a very quick, easy overview for everybody, all the stakeholders involved, to the overall outcome of the inspection campaign. I've got a video / GIF here just to illustrate how we have a software that's, in essence, pulls all those stages together. So software is called SIMS, which stands for Sonomatic Integrity Management Software. So in the top right here, you've got a number of components for the vessel. So there's several strakes, there's domes, there's vessels, there's supports here, which are listed too. So we can swap between each of these, and then the bottom left, these are all the data files for that single strake. So there's they are specified location in terms of an axial and circumferential position. If I was to scroll right, which I can't, you can also see the minimums that are associated with those, and a number of other parameters as well. And then there's also thickness distribution shown in the top right. Again, this is just to illustrate how the data is behaving. This is a much more what's called a normal distribution for anyone who doesn't know what these represent. So it's a much more smooth reducing curve. And that's very classic sign that corrosion is absent from the sample. The reason this is included is because, again, if it's behaving in a manner that in this plot I showed previously, that's much more, it's a very easy way to spot something different happening within an inspection data sample. So in other words, if corrosion is present and perhaps not being seen due to choice of color scale, or it could be quite isolated. And on a large vessel, it's very difficult to spot a small pit with the naked eye, but in terms of how it can be visualized using a distribution such as this, it's very easy to represent that. Before I move on from pressure vessels, I mentioned at the start, we tend not to consider a full asset model. So, but I just wanted to illustrate this before we move on. So one of the sister companies that we have that are owned by our parent company, a company called AUAV, who are essentially a drone inspection company. So they can go off and take a series of photographs to and stitch those together to produce an entire asset model. So we can tie into that using a platform called Insight, which is an AUAV specific software to superimpose various things on a pressure vessel model within that platform. So at the start, there was inspection data, which is overlaid. Now it's been swapped to the inspection work scope. And now this is now the liquid level of the vessel. And on the right-hand side, you'll see that's also an inspection report, which has been tagged to this vessel, which can be navigated and viewed alongside the vessel in this platform too. And there is a statistical distribution included in that in that report. Beyond that, we can essentially flatten the photographs to view the model in isolation. And what's being shown on the screen at the moment is also adding a particular area of interest with comments and make comments associated with that too. So, for example, if there's a area of pitting we want to highlight, we can mark that up on the model and and make comments to that effect. We can also append PDF reports or images to this too. And then finally, what it's about to show here is we can also add measurements to the vessel. So if there's an area of pitting, we could just add a measurement to that. What's going to be shown here is just the overall tank-to-tail length of the vessel. But again, it just serves to illustrate that we can also append the model further with other relevant pieces of information. And from memory, that's where the video ends. Yes. So moving on now to pipework data trending. So I mentioned at the start, I gave a presentation 2 years ago on our data trending methodology. I won't cover it again here. I won't bore everyone with it again. But just as a very brief overview, so we have developed a methodology for trending on spot point pipework readings, primarily because we just accept that measurement error will happen over time. So trending over a longer term mitigates that as far as possible. It also takes or gives recognition to the statistical sampling principles that at play when any kind of inspection is particularly low coverage pipework inspection such as this is taking place. So it's basically taking a representative what you feel is a representative sample of a pipework circuit and making decisions based on that. The differentiators in terms of what we do is we can identify groups of points within a pipework circuit that are behaving in a similar manner. So, for example, if dead legs are behaving one way and thicker materials behaving another, we can very easily treat those again in isolation and come up with tailored approaches for each of those groupings. We also use information on historic corrosion coverage, in other words, how widespread has corroded material been in the past, all with a view to producing more representative corrosion rates, either for a pipework circuit as a whole or for various subgroupings within a pipework circuit, with a view to feeding that into a more efficient inspection planning process in terms of are areas being over or under inspected? Should some be seeing more focus than others, for example? As I say, that's a very brief overview of the topic. If anybody wants a more in-depth presentation, please reach out to me. But again, just as how that will link into a digital format. So the image on the bottom, you'll see some blackened areas. So that's just we had to redact the one in this case pipework circuit platform names. But there's a tree format linked to the analysis. So you've got the analysis here is what's called box and whisker plots. So there's a number of different inspection years, and these essentially represent the spread of data on each of those different inspection years. Some are missing because there was no inspection in each of those campaigns. Excuse me. As I say, there's a tree format. So you'll start with a platform name, and then drop down to pipework circuit. Within that circuit, there could be other subgroupings within there, and also the corrosion rate calculations and the statistical distributions are also housed within this format, just with a view to allow an understanding for all stakeholders. So this was a static image, so just as a slightly more in-depth overview of what this can do. So we will build models in order to visualize all information. So we can we would color by a number of different factors. So in this, you'll see different colorings appearing here. So you color by last inspection, by number of times inspected. We can color by the minimum, by corrosion rate, by the normalized wall thickness. I should have mentioned previously that when we produce these type of plots, we normalize the wall thickness. So in other words, we divide all results by the nominal to allow us an easy way to compare areas within the same circuit that are of a different nominal thickness. So again, we can just quite easily represent all of those within a single model. As these things jump around, you'll see the trees, the part of the tree that's being highlighted jump around, and you'll see pressure vessels and other bits of pieces of inspection information and other things within this too. But as I say, it just serves to illustrate the ease of which we can navigate through this using a digital format. Again, just to make general understanding much more efficient. Time. So moving on now to data processing and management. So when we do an inspection, we do a digital twin will house all of our inspection data. So we've got a number of algorithms and other additional features to aid in data processing in order to deliver maximum value from inspection campaigns. I mentioned a number at the start here, so corrosion detection, in other words, algorithms can determine external versus internal corrosion. I mentioned all these already, but coating correction, batch processing, automated reporting, and additional analytics. I'm going to cover each of these in a little bit more depth now. Just as a sort of larger illustration as to how this all hangs together. So for anyone, again, for anyone who may not know, so when we perform an inspection, it's done using ultrasonics, so that will produce an image like the one that is shown on the screen. So this is a single scan file, and each of these individual pixels represents a thickness value, which is derived from the waveform data, and the waveform data is what you'll see on the top. Well, at the top is what's called the A scan, which is the signal responses. And then we've got different slices through of what's called B scan and D scan through the horizontal and vertical snapshot of the scan file. So this is used to basically the distance between the two signal responses is a way of measuring thickness at that particular location, and that's again all housed within our digital platform. So this scan here, highlighted in red, is the one that's so the scan from this slide is the one that is shown on red on this larger pressure vessel. So I mentioned the pressure vessel with a lot of data earlier in the presentation. So this is the example I was mentioning. So you can see that's where that single scan fits together in terms of the overall picture, in terms of a single strake, and also in the vessel as a whole. So this file is imported along with others into a SIMS project, which is created using the geometry, but built from in this case a G drawing. It could be a P&ID drawing up a pipework circuit. Each file is then imported, as I say, and then imposed onto the model, for a better word, and then again, it's very easy to see exactly where any gaps were. So, for example, you can see there's a number of different areas missing on this vessel. This was due to pipework. Sorry, no, this was due to walkways, and then there was an obstruction on the end here, for example. But again, this is just how the data is housed in terms before and during processing stages. So when processing on the previous slide, so in other words, when we're performing an exercise such as this, so we do have algorithms which will search. I jumped back a little quickly, but it does say what I've said is from left to right and from right to left. So in other words, we have our algorithms will search along this direction and in this direction just to search for any very subtle changes in the signal response, because that can give a very good indication, particularly in the interface signal, which is the first one, of how the degradation manifests in terms of internal versus external corrosion. I can't say exactly how it works, partly because it's proprietary, secondly because I'm not software savvy enough to explain it in enough technical detail. But we have been asked, well, what's the point if you should see if there's external corrosion versus internal corrosion? While that is fair, a lot of time we do, for example, caisson inspections where a lot of the time we can't see the external surface. We're just sending a tool down a pipe. So in that case, that does become much more value, and also in, for example, subsea inspections, we can also make much more informed opinion, I guess, on whether degradation was internal or external. So our algorithms can also account for varying coating thicknesses between repeat inspections. generally, that can be processed out. Sometimes it can't be. And I've got this best illustrated with an example, which I'll come to in a second. But the reason for this is to calculate most accurate growth rates, again, for input into integrity management decisions. Because sometimes, for example, in the example I've got, it could have resulted in a larger headache than was necessary for the client. But just to set the scene for this example. So there was a repeat inspection done by a third party on a critical item, which had significant internal corrosion, and the requirement was to determine whether corrosion was indeed active or not. Between the two inspections, new internal coating had been applied, which meant the repeat inspection resulted in significantly thicker readings. The client asked the inspection company to comment on that, and they said they had processed the coating out and therefore couldn't understand why the readings were thicker. To be blunt, the client didn't believe them, so they asked us to investigate to see what our thoughts were in terms of the variation between the two inspection campaigns. So I've got an image now just to illustrate the variance between the two. So inspection on the left hand, there's the image on the left hand side that comes from the first inspection, and on the right hand side comes from the second. These are on the same color scale, so but you can see that the data on the right hand side is shown up as much thicker than the data on the left, but the pattern of corroded material is, well, it is almost identical. So it just seems to be that the thickness readings are the issue here. So I mentioned at the start, well, slightly earlier, around how UT thicknesses are calculated. So just and just to go over that in slightly more detail. So there's 3 responses from a UT. Well, there's multiple responses, but there's 3 that are sort of important for this for these purposes. The interface signal, which is the first response, the first back wall, and the second back wall. So if I just jump back a little bit, so the interface signal is this one. The first back wall is the one in the middle, and the second back wall is one on the right. So our software can produce, in effect, 2 maps associated with this. So the interface to first back wall map, and also the first to second back wall map. The first second back wall map is traditionally what you'll see in a composite image, and the interface to first back wall is it is sometimes used, but it's much less common. However, if we take the difference between these 2 maps, we can essentially see what is a coating correction map. So again, just to use our example here to illustrate that point. So having reprocessed the data, and we were handed over CSVs of this data, so we were able to take we were handed over data files. That was OnePIS data for these for this inspection. So we produced an interface to first back wall map, and then the first second back wall map. And on the right hand side, that is the difference between the 2 maps. You'll notice a lot of missing data on the middle and the right hand images. Now we knew that the coating was new and therefore very smooth, so it shouldn't have had any deviations or missing data as a result of that. So we used interpolation and extrapolation to essentially fill in the gaps of this coating map and produce what was called a filled coating correction map. That was then applied to both campaigns, just to get the best like-for-like comparison that we could. You can see the overall outcome on both images, top and bottom, on the right hand side. So this was from the first inspection campaign, and this is from the second inspection campaign. So we were able to prove that there was essentially nothing going on in terms of active corrosion at this location. And that was just one scan file in, I can't remember exactly how many, but this one a slug catcher, so it was quite an extensive inspection that was done. So this process was repeated for multiple inspection scans. This was the worst case, and again, I thought was a good example to illustrate that point here. So moving on to the batch processing capability within our digital tools. So this was motivated by inspection that we done, which we won an award for, our sister companies along with ourselves, and produced a new technique for inspection of cargo oil tanks and FPSOs. We won the Joint Venture Technology Award at Subsea Expo last year, and also the Innovation and Technology Award at the Subsea Business Awards in Australia. So this was a replacement of essentially a visual inspection of an FPSO cargo oil tank with a UT method, which generated much larger volume of data, approximately 55,000 times more data than had been generated in previous inspection campaigns. I think we ended up with approximately 120 million data points from this inspection campaign. So given that volume of data, we had to develop much more efficient methods of batch processing in order to just to get the reporting done on time and just make everything more efficient. So again, that was all housed within a digital twin. So due to the first large volume of data, there was in effect a first pass analysis that was automated. This would just look at each file and say, essentially, is there something here that needs to be looked at or not? Is essentially how it was done as an initial sort of screening, if you like. This did reduce the amount of time that somebody would spend looking at each file during the analysis phase because settings could be applied automatically or decided in advance and applied automatically. We could calculate thickness maps, in effect push button. Any low-level noise caused by spurious signals could be removed, and files can be cached on their computer more locally for fast loading in the future, with a view to when a technician does come to look at a data file, is ready for them to do their analysis, find the minimum thickness in that area, and move on to the next one. They don't have to go through the much more laborious process of choosing settings each particular time, because very often the settings change. Excuse me, very often the settings don't change from one file to the next. So it's able to screen files with a common settings file, and then as I say, make the the analysis much more efficient. There was also a scan comments panel, which allowed information to be selected and stored with each file during the analysis phase. So we could quickly flag any common features. So there was essentially a list of checkboxes that could be added, that could be checked rather, depending on the features within the file. So if there's no corrosion, general walls, inclusions, pitting, etc. There's also a checkbox if any file needs to be highlighted and sent for review by one of our level 3s. And in addition to that, various people at the various stages could also add in any comments that they felt were relevant. So, for example, I think this is a pit, and the level 3 would agree or not, depending as the case would be. And then there was a comment box for an agreed comment that would go into the report when the auto-reporting section was run. The panel was also expanded to include a degradation classification. So in other words, is it internal, external, or both in terms of any corrosion that is present within that particular file? And in addition to that, extra properties were saved automatically with this file and carried through to the reporting stage as well, which when the inspection reports are populated. So the minimum thickness within each file and also the location of that minimum within each file were stored automatically, along with the mean and the median value of each of these files too. I just wanted to add this slide on acceptance of batch processing. To be honest, I'd be keen to hear anybody's experience with this, but from what we see, industry has been quite reluctant to accept fully automated processing, which we can understand. There's very much nervousness around human eyes not seeing the data. Yes, so people do want to ensure that the data has been looked at the very least by someone. So the point to that, I do want to stress the batch algorithms don't remove people from the processing. It's very much just a case of attempting to make their lives easier and more efficient by reducing the amount of files that has to be analysed in terms of analysed so rigorously, I suppose, best to put it. So in other words, where there is a file where no corrosion is present within the sample, that can be very quickly pigeonholed, so it can just be essentially just a check done, and then moves on to the next one. Whereas any files that flag as being more concerning in terms of there being corroded or degraded material within that file can be flagged and analysed as required. So what I've got here is, again, another GIF which will cycle through a number of different aspects to this. So this is the digital twin that was built for this FPSO. The areas in green are those that were inspected from this particular, of that particular cargo oil tank. So you'll see from the images as they filter through. So these are just changing by files that were flagged for analysis, covered by thickness values, whether or not there was internal, external defects, or both within those. So again, it's just another way of showing there's how easy and how straightforward it is to represent multiple different aspects of the parameters of each file and the findings of that. at the touch of a button. Again, this was handed over to the client, and they were very happy to see such an easy way for all stakeholders to visualize the various different aspects to the inspection. I also mentioned automated reporting. So given again the sheer volume of data, we had to automate our reports just again because it was easier to spit them out rather than go through a process of building a Word document for each one. So given everything that was done in the automated processing stages, all that was pulled through into an automated report at the end. So each tank had approximately 275 scan files, and there were 1,102 files altogether. So these were pulled into what you've seen here is essentially what was called a one-page summary, which was what the client wanted of each of these particular files. So you've got just the file stats, in other words, the name, location, the nominal thickness, the minimum that was recorded. It's highlighted within this grid to show exactly where on this component that file was taken. There's a defect classification, if there is any, so internal, undefined, external, for example. The thickness map will show that particular scan file, and also essentially the all other files close to it, and how it fits into the bigger picture. And finally, any reports that were made against that particular file also carried through into the automated report. So I should have mentioned this diminution, which was a class reporting requirement, was added to. So it's just a yes or no. Is there any diminution present within that? That was required for the class society, which look after the shipping accreditation. They required that as to be included in the reports. So we could also generate a second report for any specific file that was of particular interest. We could have more focus on the minimum thickness and a profile of the wall thickness. It's maybe not that easy to see in this image, but there's a profile plot, so you can just about see here the profile running through the horizontal and vertical slices. You'll see that there's much more variation at the right-hand side here, where you go over this area of corrosion. And again, similarly in the vertical slice, you can see it's probably more visible there. You can just see the vertical profile as you move through the sample size, and then there's a drop off as you cover that area of corrosion. So again, just a much more quick and easy way to represent various different aspects. We could, in addition to this, split up areas with different nominal thickness, because very often we would cover an area where two plates have been bolted together of different nominal thickness. So we could again split those up if necessary and produce separate reports for each of those. And then, in addition to all that too, we were also asked to represent summary tables. So just to give a very quick snapshot of each of the various frames within the cargo oil tank. So frames A to B, there were 38 files. The number of data points that was in that, whether or not there's any percentage diminution, number of files that were flagged during the analysis phase, and the number that were flagged as having no corrosion. So as I said, it's really just a means of breaking everything down to area by area. So it gave the client a good snapshot of any areas that were maybe behaving slightly differently to others. So for example, frames D to E had 5 files flagged for the analysis compared to 1 or 2 for all the others. So they may choose to put more focus on frames D to E in the future. But that was very well received by the client. I've got a speech bubble showing what they said here, but they just they were really did appreciate how succinct and cleanly they were able to understand the data that was collected during the inspection campaign, just given there was so much of it. So finally, the additional analytics. So this is a snapshot of essentially defect matching software. So if we have the 2 repeat inspections, we can match defects between one inspection campaign and the next. We can compare those to assess any changes to either the depth or the dimension of the defects. Just quantify any changes between the inspection in terms of growth, as I say, in terms of either axial or longitudinal extent or depth. We can trend on any individual defects. So if there's 1 or 2 that are of particular concern, we could isolate those and see if they're behaving differently to the inspection sample more generally. We can also export these corrosion maps into the cumulative thickness distributions that I showed earlier to perform a more detailed statistical comparison, be that either comparing the thickness distributions directly, or we could perform a more in-depth statistical analysis, which would be driven by the data and what particular things are. But some things we can do is we can do nearest neighbour comparisons, point-to-point comparisons. We can do Bayesian analysis, we do regression of the various different things. So that is a whole different presentation itself, which I'm not going to cover here. But as I say, just to give an additional flavour for the types of stuff that we can do with repeat inspection campaigns. Okay for time. But just as a summary now, so digital tools will improve consistency, accuracy, understanding, repeatability, and decision outcomes for inspection campaigns. Just due to the ease it is of housing all the data and visualizing it for everyone. There are a number of digital solutions that can be developed, deployed, including 3D mini twins, digitized flow charts and calculations, batch and automated reporting. I hope I've shown that the canal of integration is quite simple and also complex tools. And then finally, digital tools will facilitate one, a detailed analysis of inspection data, critical to integrated decision making. So in other words, deriving maximum value from your data. And secondly, I think it does also recognise a more general point that there seems to be a more growing need for data analytics capability and integrity teams, given, as I say, the vast volume of data that are being generated now, and the increasing interest there is in making better use of that data. So that's everything from me. I hope you found it interesting. I'm happy to answer any questions. I think I did okay for time.
Well, thanks very much for that, Kevin. That was fantastic. Good timing as well. We've only got one question here, and that's from Zubair. And it is about how large are the files for the scans and how big can it get for a vessel? Guess quite large because of storing all of the scans.
A single scan file typically, it can range from about 200 megabytes up to a gigabyte. So when you've got all that, if you've got a vessel that required 100% inspection, that can be a lot of data. Is the short answer. Yes, I'm not sure about the file size of the vessel itself, but yeah, so typically a single scan file is in the region of 200 meg to a gigabyte. Is that okay?
Yeah, I think so. Yeah, you can see from your description, it's a lot of data that's required. So yeah, no, thank you very much. I think that was all of our. Oh, we've got another one here. Sorry. Again from Zubair, just saying, not sure if he noticed it right, but when filling the coating correction, it was the filling where corrosion trend was because of no signal from the second back wall. So this implies that interpolation is being done where the corrosion product does this decrease uncertainty.
So it's make sure I understand. So the missing data. Well, reshare. So I'll put the slide back up. So in this slide, I assume is. So basically, there's missing data here, and that's being interpolated. Is that what the question is?
I believe it's to do with this coating correction and about filling in where the corrosion trend was and saying maybe just because of no signal from the second back wall.
Yeah. So the short answer is yes. So when you've got corroded material, the signal from the second back wall does tend to be much more limited. So which are, well, in other words, it's much smaller because the reflection is much smaller because of the corrosion product. So that will be what's caused a lot of the missing data in this instance. But when you take the difference between the two, this really is just a means to estimating the level of the coating rather than the corrosion itself. That answer the question?
Yeah, I think it's just to ask as well if that decreases uncertainty, having to use a bit of interpolation at that section.
I mean, yeah, so the interpolation will be, it's basically, without going into too many specifics, it's governed by, it's in effect a nearest neighbor interpolation. So we can go by what's around the missing pixels to determine the most likely value within that. Because we're just looking for a coating map. Where this external degradation, for example, we wouldn't be able to do that because we wouldn't see with any certainty what was in there. But yes, it is with a view to decreasing uncertainty, because we knew the condition of the coating. We just needed to take account of that in terms of the missing data points.
Perfect. I think that maybe answers the point. Got another question just asking, how long does it take to prep for a digital twin driven inspection?
We can build a digital twin. Well, the models we showed, for example, for a Persian vessel, we can generally build those in a few minutes. Again, with pipework circuits too, they're generally very quick to build those. And the only times these sometimes do take a little bit longer is if you've got a vessel that's got a lot of nozzles on it, for example, or if it's a particularly unusual shape. The one I showed at the start, which had a tapered section. Here, so this one was slightly more awkward to build because of the taper section. You get vessels that have, for example, boot sections, which again can be a little more complicated. But in general, half an hour at most to build a model like this. So that's then handed over to the inspection team. I assume that's what the question relates to. If it's prep work for the actual physical inspection, to be honest, I don't know.
I believe so. I think we've got another couple of questions, and I think after those ones we'll have to just call it a night because it's already 7. So the next one is, how does the inspection technique (brackets corrosion mapping) account or compensate for structural discontinuities, say appurtenances or saddle supports?
Sorry, can you repeat the questions?
Yeah, so how does the inspection technique, so the corrosion mapping, account for any structural discontinuities such as appurtenances or saddle supports?
So we couldn't inspect saddle supports. So, for example, if we want to inspect an area underneath a saddle support, we would deploy different techniques such as chime or multi-skip. So it can't be used in those circumstances. And very often, we would recommend an alternative technique if there any kind of discontinuity that was of concern.
Okay. And the final question is, how do you ensure data integrity and reliability in digital inspections?
Just by the data is always, when data has been collected by the inspection teams, they are constantly feeding data back to us, so we can essentially screen it for quality. And if it's particularly noisy or if there's a lot of missing areas, we would ask them to repeat that area. But I think so data is in effect continually screened in terms of when it's being collected.
I think that's all of our questions for tonight. So thank you very much for the presentation, Kevin. I don't know if anybody has any other questions, if they can maybe just contact you directly
Yeah, of
after
course.
this.
Yeah.
Perfect. No, that's fantastic then. Thank you very much for that.
Thank you.
We will close off our webinar, and we'll see you at the next event, which will be our industrial visit. So thank you everyone for attending. Goodbye.
Thanks. Bye.